All right, let's dive in. Today, we are opening what might just be the biggest cold case file in all of history, the search for extraterrestrial life. I mean, it's the ultimate question, right? Are we alone in the universe? And if we're not, what should we actually expect to find out there? Let's start the investigation.
So, first things first, in any investigation, you gotta survey the scene. And wow, the number of potential locations is just exploding. As of right now, astronomers have confirmed nearly 6,000 planets outside our solar system. And that number, it's going up practically every single day. Every one of those is a new place where clues could be hiding.
And that massive number of planets, well, it kicks off what is, no joke, the greatest detective case in human history. We're looking for life. But like any good detective knows, before you can find your suspect, you have to know exactly who or what you're looking for. Okay, so Section 1, defining the target. Every good investigation starts with a profile of the suspect, right? So before we can even begin to find life, we've got to agree on what life even means.
Now, you'd think this would be simple, but there's actually no single perfect definition of life. But scientists do have a kind of working checklist. A three-point test, if you will. To be considered alive, something has to do all three of these things. First, it has to have metabolism. That's just a fancy way of saying it can take in energy and use it. Second, it has to be able to copy or replicate itself, to grow and reproduce. And third, it has to be able to adapt and evolve over time. Okay, so that's what life does, but that's only half the story. The other big question is, what is it made of? What's the chemical blueprint? Because, the building blocks themselves are absolutely crucial. And as far as we know, all life here on Earth is based on one very, very special element. When it comes to the chemical foundation of life, you really hear about two main contenders, carbon and silicon. But honestly, it's not much of a contest. Carbon wins, hands down. First off, it's about 10 times more common in the universe, so there's just more of it to go around. Its chemical bonds are also stronger and more stable, which is perfect for building the long, complex molecules life needs. But here's the real kicker. When carbon bonds with oxygen, it creates carbon dioxide, a gas. That gas can dissolve in water and move around easily in a biological system. Now, what happens when silicon bonds with oxygen? You get silicon dioxide, which is, basically rock, sand. Not exactly ideal for life. And this classic line from Star Trek just nails it perfectly. I am a doctor, not a bricklayer. A silicon-based life form would basically have to metabolize rock. Imagine trying to run a biological system with little bits of sand floating through your veins instead of, say, dissolved CO2. It's not going to work for the super fast, complex chemistry that life depends on. So our suspect is definitely carbon-based.
All right, Section 2, the cosmic habitable zone. So we've got our suspect profile, right? We're looking for a carbon-based life form that can metabolize, replicate, and evolve. So the next logical step in our investigation is, where is this thing most likely to be hiding? It's time to stake out the neighborhood. So just like any living thing we can imagine, our target is going to have some basic needs. First, you absolutely need a liquid of some kind, what scientists call a solvent, to move stuff around inside a cell. And water, it's called the universal solvent for a reason. It's just amazing at this. Second, you need the raw materials, the building blocks, so plenty of carbon, hydrogen, oxygen, and so on. And third, you need an energy source to power the whole operation. That could be light from a star or maybe chemical energy from deep-sea vents. Without these three, it's a non-starter. But, just finding a planet with all that stuff isn't enough. The neighborhood has to be safe. And in space, the whole neighborhood is defined by its star. So what's the best kind of star for life? Because believe me, not all stars are created equal when it comes to being a good host. Think of this as your cosmic real estate guide. On one hand, you have the massive hot stars. They're super bright, but they live fast and die young. They burn out way too quickly for complex life to have a chance to evolve. On the other end, you've got red dwarfs. Now, these guys are the most common stars out there, and they live for trillions of years. But they're really unstable. They blast their nearby planets with these intense sterilizing flares. So that leaves us with the just right stars in the middle. The sun-like G and K-type stars. They're the Goldilocks choice, offering billions of years of stable, steady light and heat. Perfect.
And even with that perfect star, the planet itself has to be in the perfect spot. I mean, it's all about location, location, location. If you're too close to the star, all your water just boils away into space. If you're too far out, it freezes into a solid block of ice. That perfect little orbital ring in between, where the temperature is just right for liquid water to exist on the surface, that's what we call the habitable zone. Okay, on to section 3, searching for fingerprints. So let's recap our investigation. We have a detailed profile of our suspect, carbon-based life. And we've staked out the most likely location, a planet in the habitable zone of a sun-like star. Now it's time for the really hard part, searching for actual, hard evidence, the fingerprints. Obviously, we can't just send a probe to these planets. They're light years away, so we have to do our detective work from a distance. And we do that by looking for something called a biosignature. It's exactly what it sounds like, a signature of biology. Think of it as the chemical fingerprint that life leaves behind. And the best place to find that fingerprint is in a planet's atmosphere. So what are these fingerprints? Well, they're specific gases in the atmosphere that shouldn't really be there in large amounts without something constantly making them. We're on the hunt for things like oxygen, ozone, or methane. And the way we find them is incredible. We use powerful telescopes to watch as starlight filters through the planet's atmosphere, and we can analyze that light to see what gases are present. But here's the real smoking gun, the holy grail of biosignatures. It's finding oxygen and methane together. Why? Because these two gases just hate each other, chemically speaking. They react and destroy each other. So if you find them both hanging out in the same atmosphere at the same time, it means something. Some process must be constantly pumping them out. And you know what the best explanation for that is? Life. All right, final section, the most likely suspect. We followed all the evidence. We've built a profile, we've identified the location, we even know what fingerprints to look for. So after all this detective work, it's finally time to reveal our most likely suspect. And to do that, we have to look at the only case we've ever solved, planet Earth. The final and maybe most important piece of evidence comes from right here at home. Check out this cosmic calendar. If you squeeze Earth's entire 4.5 billion year history into a single year, Earth itself forms on January 1st. The first really simple life shows up pretty early, around March. But look at this. You don't get the first multicellular life until October. And us, humans, we don't show up until about 11:40 p.m. on December 31st. We're a last-minute party crasher. Just let that sink in for a second. For over 3 billion years, for the vast, vast majority of time that life has existed on this planet, it was all just simple, single-celled stuff. Bacteria, algae, slime. The kind of complex, intelligent life that we are is an incredibly recent arrival on the scene. A blip. And that might mean it's also incredibly rare. So after our whole investigation, what should we really expect to find out there? All the evidence points in one very clear direction. The odds are stacked against finding little green men or sprawling galactic empires. Instead, the evidence points to something far more fundamental and probably way more common. Life in the galaxy will likely be abundant, and with our new telescopes, it will be detectable. But it will most likely be simple slime. And you know what? That's still an absolutely incredible discovery waiting to happen. It's not a question of if we'll find it, it's just a question of when.